All right, let's take a look at activity 3.5.3, kind of a long one, so we'll try to break it up a little bit. I've broken up the questions a little bit more than the textbook did, but let's see how this is going to work. So we've got a camera tracking a rocket, and the camera is 4,000 feet from the base of the rocket. We assume that the rocket is moving vertically. So actually, before we even do anything else, let's see if we can draw a picture of what's happening there. So a camera is tracking a rocket, and it is 4,000 feet from the base. So it's going to be a big triangle, right? And so my camera is down here. Here's my rocket. Okay, and let's see, the height of the rocket, of course, is going to be changing in time, so we'll put an H there. And then this is the distance from the camera to the rocket. That's going to be changing. Instead of using D, let's go ahead and use Z maybe. That's the distance again from the camera to the rocket. And now the distance from the camera to the rocket from here, is that changing or is that constant? I believe that is constant, right? That's the 4,000. Okay, so we don't want a variable down here. We want to put that as a constant, 4,000. Okay, and then here's the angle that the camera is making with the rocket, okay, or with the ground, I guess you could say. Good, so that's a good picture of what's happening. Now let's go back to the question. Find a relationship between the height of the rocket and the angle between the camera and the rocket. So is there a relationship between the height of the rocket, that's h, and the angle between the camera and the rocket? Right, that's going to be theta. Good. So is there a relationship here? Well, of course it's a right triangle, so there's lots of relationships between these three numbers and theta. But since z is an unknown, let's see if we can avoid using z in our formula. And so if we use if we have opposite over adjacent, right, that's going to be the tangent. And so let's go ahead and use the tangent function. And so let's go ahead and write then that the tangent of theta. And in fact, we could go ahead and say theta and h are functions of t. So theta of t is equal to h of t divided by 4,000. Okay, good. So there's our relationship between the angle and the height. And now can we find a relationship between the rate of change of the height and the rate of change of the angle? Well, sure, that's just differentiating this angle. So this, by the way, we're in the section of related rates, right? So therefore, is the rate of h of t and the rate of theta of t, the rate of changes, are those rates of change related? Yes, they are. They're related through this function. Good. So then we'll differentiate both sides of this with respect to t. So the derivative of tangent would be secant squared of theta of t. And then you have to multiply by the derivative of your inside function, d theta over dt. I'm writing it as a fraction like this just to emphasize that we're differentiating with respect to t, is equal to the one, you could think of this as like 1 over 4,000 times h. So the 1 over 4,000 is just a constant, right, times your h of t. And so the derivative is just going to be 1 over 4,000 times dh over dt. Okay. Now, just to make this a little bit simpler, yeah, I guess we could have multiplied through by 4,000. You didn't have to. But this gives us an easier relationship, perhaps. dh over dt. Good. So this was parts A and B so far. Good. Now part C. Find a relationship between the distances between the camera, the rocket, and the ground. Of course, we have a right triangle. So what is the relationship between those three numbers? Ooh, my ink is still wet. That's the Pythagorean theorem. So we have that h squared plus 4,000 squared is equal to z squared. And also I should again remember that h and z are actually functions of time, right? So this you might be it might be clearer to write this as h of t squared plus 4,000 squared is equal to z of t squared. Okay. So now you can probably guess we're going to be differentiating this. So let's just go ahead and find the relationship between these rates of change. So let's go ahead and this is kind of an additional find the relationship between dh over dt and dz over dt. Is there a relationship between those? Yeah, we can just go ahead and differentiate directly. 2 times h of t times dh over dt. Did you remember to multiply by their derivative of the inside? Is 2 times z of t times dz over dt. Good. And you know, we might as well simplify a little bit more. The 2's would cancel out, and so you're just left with h of t times dh over dt is equal to z of t times dz over dt. Good. So this is now our relationship between the height and the distance to the camera. Good. Now, if the rocket is moving at 600 feet per second when h is 300, find the rate at which the distance between the rocket and the camera is changing. So how would we translate this? If the rocket is moving at 600 feet per second, what is that in terms of our picture? Yeah, the rocket is moving up 600 feet per second, so that is actually dh over dt. So part D says that if dh over dt is equal to 600 when h is equal to 300, find the rate at which the distance between the rocket and the camera, find dz over dt. Good. Oops, I think that was supposed to be 3,000, not 300. That was a typo on my page here. This should have been 3,000, not 300. Okay, sorry about that. Good. That's because when I plug h equals 3,000 in, right, I get a nice triangle. Right, because if this is 3,000 and this is 4,000, then this is a 3, 4, 5 triangle, and so that's be 5,000. If you didn't know that, right, you could just compute z using the Pythagorean theorem. But it's a nice relationship there. Good. Okay, so let's see. Let's plug things in. So h is 3,000. dh over dt is 600. And then z of t was 5,000. And then dz over dt is the question, or is our unknown. Good. So it looks like 3/5 times 600 is the answer. Let me go ahead and compute that. 3/5 times what? 600? 360. So dz over dt equals 360. 360 what? Did you say feet per second? Good. All right. So that's part D. Let's see. We have one more part here to think about. Oop. Let me get rid of this thing now. Okay. Oop. At the same moment as this one, find the rate of change of the angle between the camera and the rocket. So we want to find d theta over dt. So let's summarize what we have here. Right, we have this relationship is where we computed our d theta over dt, and now we know what dh over dt is. So we found that dH over dt was 300, oh, that was dz over dt. dH over dt was 600. And so we want to find d theta over dt at that moment when h is 3000. Okay, so let's go ahead and write that down. So let's get a new page here. We want to find, so we have 4000 times secant squared of theta of t times d theta over dt is equal to dH over dt. And we were told that dH over dt is 600 feet per second. That's the speed of the rocket. And now we want to find d theta over dt. So this is our unknown. And we know that at the point in question, right, here's our theta, we had the triangle was 3000, 4000, and 5000. Good. So I don't need to know theta because I know what the values are on my triangle. So what's the secant? The secant is 1 over the cosine. The cosine is adjacent over hypotenuse, so therefore the secant would be 5/4. So in fact we can say 4000 times 5/4, or 5000 divided by 4000 squared times d theta over dt is equal to 600. Good. Does that make sense? So I'm just plugging things in here. The 5,000 over 4,000 is the secant. It's the hypotenuse over adjacent. Now these are not fixed values, right? We were told that the instant of time that we want to evaluate this, h was 3,000 feet. Okay, that's how I knew what those numbers were. Okay, so now we just plug things in. One of these 4,000s will cancel with that 4,000, so that will leave 5,000 divided by, or that'd be 25,000 divided by 4,000, and then divided by 600. Oh, wait a minute, I wanted to move the other direction, didn't I? Hey, okay, let's try that again. I should have written this out first. So d theta over dt is equal to 600 times, and now that was going to be 25,000 over 4, so that would be 4,000 over 25,000. Good. Let's see, what do we get from that? Well, the thousands of course cancel. 4 over 25 times 600. Let me compute that. Let's hang on for a second because I want to be careful about squaring these. Because 5,000 squared, right, isn't 25,000. So let me redo that. In fact, let me simplify that before we go any further. So 4,000 times, now this is 5/4 squared, so you can just cancel off those thousands, right? So that's going to be 25 over 16. That's going to be easier to compute. Times d theta over dt equals 600. That's easier to do. Okay, now our d theta over dt is going to be 6 over 40 times 16 over 25. Good. I think that's equal to 0.96, and that is radians per second. Radians per second. Very good. All right. So that finishes up that problem. Once again, we're at like 15 minutes. So, yeah, these problems are kind of long. Okay, we'll try a new one.